Welcome back, everybody. This is the first video in the testing module, which follows the implementation module. And what we're going to be doing is building off of the stuff that we've already talked about in the, I guess at this point, almost 5 previous weeks. So up to this point, what we've talked about is getting with the client and kind of understanding what the requirements of their system are. Trying to figure out what they currently do and how you're going to be replacing what they currently do, either with a brand new automatic system or with a different automatic system. Then translating all of that analysis into a technical specification, and then from that technical specification, actually implementing all of the code that gives you the system that they are requesting. So as you may have experienced in your life, I know that I have experienced it many times over, you're not going to necessarily get everything right the first time you do implementation. And so what we're going to talk about this week is the testing workflow or the testing phase, which basically goes through each of the pieces that you have implemented and make sure that there aren't any defects in them. So the entire idea of testing is to make sure that you are aware of all the problems in your implementation and you have some kind of even rudimentary understanding of how to address some of those issues. Now, one of the things that you might have sort of assumed by this point is that testing is only really relevant to implementation, but you can actually test all of the documents and all of the artifacts that you've created thus far. So there could very well be defects in requirements, there could be defects in your design, there could be defects in use cases and diagrams and bug reports and all sorts of stuff. And the testing phase is really trying to get at the heart of all of those defects by finding defects in the code that you can trace back to some of these other things. So if there's a bug in the code, it could be because the code is bad, or it could be that the code is actually built on a requirement that is bad or a use case that isn't fully understood. So the two kind of big types of testing, and there are a lot of ways to cut testing up. And so I wouldn't get too caught up in the different types of testing and how you can kind of subdivide it into types and approaches and all that kind of thing. What I would really be focused on is what each of these kind of buzzwords means. And so automatic versus manual kind of makes sense, right? So manual testing is kind of the de facto way that you've all been doing testing for your programming assignments from the very beginning of the program, right? So you write some code, you walk through the code yourself, and you identify anytime you get behavior that you didn't expect. So either the application doesn't do something that you think it should, or it does stuff that you don't think that it should be doing. There is also automated testing, and there are a whole bunch of frameworks around automated testing, be it unit testing or automated integration testing. And the idea is the entire point of what you're doing as a software engineer is taking a bunch of jobs that are really kind of mundane, and you're trying to codify them to the point that those jobs can be done over and over and over again with as few issues as possible. So they're trying to make, or you're trying to make, technologically repeatable processes. And so what automatic testing is doing is it's making software testing an automatically or technologically repeatable process. What you're trying to do is make sure that a person who is testing your system has to have as little information or knowledge about the system as possible, and what they are testing is a small subset of the whole application, and the majority of the rest of it is tested by some code somewhere. So what you're looking at here is kind of a trade-off, right? Manual testing is very, very dynamic. A user is much more likely to be able to react to changes in requirements or changes in expected behavior than automatic tests are. And so if you have a bunch of requirements that are constantly changing, and that means that the behavior, the expected behavior is changing, and that means that your automatic tests will also have to change. So it really all goes back to those metrics that we talked about around requirements and around use cases and things like that. As your system becomes more and more stable and less volatile, automatic testing can save you a lot of time because you won't necessarily have to redo manual testing. You can click a button and then let essentially a robot do the testing for you. Another kind of way that you can split up testing is by unit or integration tests. And so unit tests are basically tests that are run on an individual building block of code. And so you can think of these individual building blocks as units. A lot of the times these things map directly to functions or to methods. And ideally, you should be able to very clearly delineate the mapping between units in your code and units in your architectural design. So there should be some map, even if it's implicit, where you can easily understand what amount of unit test coverage you have in your whole application, and that is a result of your ability to decompose your application into sub-pieces, which was sort of the big thing that we talked about in design. So integration testing is the other side of that. So unit testing allows you to test a whole bunch of units. Integration testing allows you to test the space between those units. And so what you're going to do is you're going to take maybe three to five units. You're going to make them communicate with each other, even if it's an artificial communication. And you're going to test to make sure that the communication flows between those units correctly, and what you get at the end of the process is correct. So you can think about it, if we go all the way back to our construction concept, you could think of unit testing as testing bricks to make sure that the bricks are stable, and integration testing is testing a component of a brick wall, making sure that the mortar between those things is correct, making sure that all of the bricks hold their shape and that kind of thing. What you can easily do with integration testing is you can also test the interface between your application and third-party APIs. And doing so can help you a lot because, as we talked about last week, the interface between your application and a third party, or an interface between your subsystems inside of your app, are the most frail things, or the things that are most likely to have breaking changes in them. So if you can identify when these breaking changes occur with automatic testing, that will save you a lot of time and effort, especially if you're able to very early detect these things. So you can obviously tell that the different ways of breaking down testing, these things are not mutually exclusive, right? So you can have a full suite of automatic tests for unit testing and automatic integration tests. And ideally, what you would have is 100% automation in your entire code stack. And what that would mean is every time you made a change and you checked in your code and you built your code, you would know if there are any bugs in your code because everything is automatically tested. The issue is that this is almost impossible to do, and practically you will spend more time and effort trying to maintain the tests than you will trying to maintain the code, because ultimately the entire development system is built to be agile, and the more agile you are, the more likely your tests are to be out of date. On the opposite end of that, there are a lot of companies and a lot of organizations that are looking at what is called test-driven design. We've talked about that a couple of times in the class already. But basically the idea is that you can start off development by being very focused on unit testing. And so in order to implement test-driven design, what you do is you have all of your code or your system decomposed into small code pieces. And then you build a unit test, and that unit test kind of encodes what your expected behavior is. And then you code a piece of code that ultimately is iteratively refined until it passes that test. And so you know then that that piece of code exhibits the expected behavior, because the expected behavior is captured in the original unit test. So it's a really good idea to have test-driven design, and it is particularly useful for things like framework components. So if you have a piece of code that's going to be used by a whole bunch of different people, it's good to know that your subsystem, your framework subsystem, is decomposed to the point that you can easily write unit tests on it. That by itself is very beneficial, even if you don't have testing over all of the different components. There are a lot of problems with the approach, particularly with applications that are in constant flux. So if there are just tons and tons and tons of requirements changing all of the time, then it's going to be really hard to implement test-driven design, because you're going to really struggle trying to pin down what the expected behavior is. So the anecdote that I have, they usually go along with this part of the class, is that I once worked on an application that was really for time capture, and I worked on it for a very, very long period of time, several years. And maybe a couple of years in, there was a huge push to adopt test-driven design. And the problem with that is you've already created a whole bunch of code, and you're maybe 100,000 lines of code in, or 200,000 lines of code in. You can't easily go back in time and write a bunch of unit tests and then write a bunch of code that passes those unit tests. So if you swap from a standard design model to test-driven design, what you find yourself with is a whole bunch of architectural debt that you have to pay down before you can actually achieve test-driven design. If you're in a situation where you need test-driven design to ensure that everything is tested, potentially that payoff is there. You're going to get something in the end that is going to be worth the reinvestment of time to do the refactoring that's required to pay off the architectural debt. In a lot of cases, and specifically in this anecdote, that is not necessarily the case. The second really big problem that you're going to run into is the fact that a lot of actual architectural designs themselves are innately not unit testable. So if you've ever heard of the singleton pattern is notorious for not being easy to unit test. And the reason is that the singleton pattern itself kind of hides its internal state in a lot of ways. And so having a singleton that is accessed by a whole bunch of different units kind of makes it difficult to test those units unless you have kind of cleverly mocked that singleton class. So you can run into some situations where legacy code makes it particularly problematic to implement test-driven design. So if you're interested in test-driven design, it's best to kind of implement this thing from the ground up. So the first kind of pass at the application, if you're interested in test-driven design, it's much easier to implement than trying to come back after the fact and implement it. So one of the things that you want to do is you want to make sure that you're performing incremental testing, not necessarily only on code, but on the entire sort of stack of artifacts that you're creating along with your application. So once you are creating these kind of like low-leveled, very tightly coupled components that a whole bunch of people are trying to use, automated testing is great, and test-driven design is basically the gold standard. And the reason is if you make a change to those components, you could very easily break a whole bunch of different stuff. And if you have automated testing, you will kind of instantly know that you've made a breaking change, and then everybody will be alerted that everything's fine, and then somebody will come in and try to fix it kind of immediately. If you are also looking at this kind of mapping between units and use cases, and you can kind of have a one-to-many or a one-to-not-very-many relationship between requirements and code units, it's also really easy for the business team to look at those units and tell you which ones are the highest priority, and then you can take those highest priority ones and write automatic testing for them, and not necessarily all of the requirements. And so one of the sort of key ideas of this first video, or this first part of the testing module, is about how you can't really easily test everything top to bottom. If you have some way of intelligently prioritizing your testing effort, it is going to make your life easier, and you're going to end up with something that is tested around the most critical components, and that is a much better situation than ending up with a project that isn't tested at all. So ultimately, you're going to try to test a whole bunch of stuff. And if you try to test everything, either you're going to fail or you're going to spend too much time trying to test everything. If you can prioritize either with help from the business team or through counting bugs that are associated with a piece of code or whatever, that prioritization is ultimately going to help you a whole lot. One of the things that are important in prioritization, and we're actually going to talk about this toward the end of the module, is that if you are checking in a piece of code, you want to be able to link that piece of code with a test or with a requirement and with a bug. And so what that allows you to do is prioritize based on code metrics or metrics that are inherent to your repository, not necessarily solely based on what the business team is telling you. So what you're going to find, and what research shows, is that if you have a piece of code that has had a bug in it before, that piece of code is more likely to have bugs in it in the future. So you will find there are basically like these energy wells of time that you'll find in the application. There'll be a class or a handful of classes that perennially have the most bugs in them. And so what you want to do is keep a track of how many bugs are in a specific piece of code by establishing these kind of links. And so if you've seen in open source software, very often there will be a bug ID that's in the commit message of every commit. That's one very common way of linking between a bug repository ID and the actual commit SHA in your repository. You can do it however you want. The point is that for best practices, you need the link, and you need the link because ultimately you're going to use that data in the future to make decisions. So you're going to say, this piece of code has had 50 bugs every time we've released the software, and so because that class has had 50 bugs, we're going to prioritize unit testing of this piece of code, and we're also going to make sure that the testers are heavily testing the functionality around this piece of code before we push out a change. At the end of the day, what you want is the highest level of testing effort, so automated testing or manual testing, unit testing or integration testing to be performed on the pieces of the system that have the largest amount of critical business function to them and are the most likely to be defective. So the pieces of code that are the largest and the pieces of code that have had the most historical bugs associated with them. So manual testing itself is obviously going to be the most common form of testing, and the textbook outlines two primary forms of testing, or manual testing, and we're going to talk about the second of these kind of at the end of the module. But it separates manual testing into execution-based and non-execution-based testing. And so execution-based testing is literally running the application and then sort of sitting at your keyboard and then interacting with the system and making sure you get the behavior that you expect. Non-execution-based testing doesn't require the code to be functional at all. And what it really is something closer to a code review. So you're sitting down and you're reading the code kind of in depth. And through this analysis, sort of stack analysis of your reading through the code, you can identify potential things or potential downfalls, or you can look and see that there's defensive code that's missing or there are corner cases that you've missed, and you can add those things after the fact. So the textbook also makes a point of talking about quality assurance teams, and a lot of large companies do have large quality assurance teams. This is a type of team that are sometimes software engineers, other times they're support techs, and what they do is they are solely responsible for testing everything kind of top to bottom. The problem with this approach is often that if you have a large quality assurance team and that quality assurance team is very highly regimented, engineers themselves will become less likely to actually test their own code, and so it becomes very easy for an engineer to kind of pass the buck and say, bugs aren't really my problem, there's somebody else's problem, and then coding standards usually dip. You typically have more unstable framework components, particularly, especially if your QA team is more on the support side than the engineering side and doesn't necessarily have the visibility into the code that they need to actually fully test a framework component. So if you can kind of put yourself in the shoes of an engineer who has a huge quality assurance team to fall back on. If you've never tested your own code and you have never been responsible for a problem that was caused by your untested code, it's very easy for you to kind of point fingers at the QA guy that says, and say, hey, it's his fault for not catching the bug, instead of your fault for not actually doing best practices and doing your job correctly. So we talked a little bit about prioritization, and so like I said, prioritization is the most critical thing about testing. You could very well spend years and years and years testing an application before it goes to market and not find any issues with it. And the problem there is you spent all this time in testing and you haven't earned any revenue on the application that hasn't gone to market. It's just sort of sitting in the garage being tested. If you try to do random testing, this is kind of the worst possible way of doing things, because what you're ultimately going to end up doing is you're going to start testing the pieces of the application that people are the most familiar with. And if you are testing the pieces of the application that people are the most familiar with, you're testing the most solid components of the app. So what you really should strive to do is you're trying to find the most esoteric use cases. You're trying to find the easiest ways to break the system, not give yourself selection bias or internal bias that says if I don't find any issues in testing, then my code is perfect. Because we've all felt that, but we also recognize that that isn't necessarily true. So test case selection itself obviously becomes a much larger problem the larger your code base gets. So if you're looking at 10 million or 12 million or 15 million lines of code, you obviously can't test all of that top to bottom between minor releases. So test case selection is basically the idea that you're going to test maybe 35 or 40 or 50% of the application, and you need to carefully select the pieces of the app, be it code, classes or methods, or use cases and requirements. You need to select those such that the most critical and the most likely to be faulty things are actually tested, and the most solid pieces of code and most solid pieces of functionality are kind of left to their own devices. So if you have started the whole process with a really nice list of functional requirements, which you're hopefully working on right now for the first iteration, and you have prioritized those functional requirements in such a way that you kind of know what is a stretch goal and what's the absolute most mission critical thing for the application, you can obviously use those prioritized functional requirements to help you with test case selection. You would say, pick the top half of the list, and we're going to go through these in great detail and test every component of them. And if all of those pass, then the bottom half is kind of okay. We recognize that these pieces of functionality are only used by maybe a subset of the users. And if there is a critical bug, we can always go and fix it as fast as possible, but it's not going to be the end of the world if a bug is found. So obviously what you want is you want framework components, you want things that are interdependencies, you want those things to always be prioritized, and then again you want to prioritize things that the business team is looking for, and you also want to prioritize things that you know have historically been problematic. They've been brittle in the past. So next time what we're going to do is we're going to talk about the two kind of approaches or the philosophies behind testing. One is glass box and the other is black box testing. The idea behind glass box testing is that you're going to test based on code. You're actually going to look at code and you're going to use code and enumerate code to kind of understand all of the different units that you need to test. Black box testing is the exact opposite. You're going to use requirements, or you're going to use use cases or specifications, and those are going to be enumerated to outline exactly what you need to test. Instead of testing methods, you're going to be testing use cases, so on and so forth. So thanks very much for listening, and I hope to see you in the next video. Thanks.